Okay, picture this, a full-blown planetary rover. I'm talking real satellite data, a mission control dashboard, the whole 9 yards. But what if I told you it wasn't built in some billion-dollar lab? Nope. It came from a university workshop in Cape Town. One student did it. So let's get into exactly how he pulled this off. I mean, seriously, this looks like something straight out of NASA's art department, right? A mission poster for the next big expedition. But here's the kicker. The 𝗙𝗏𝗏 rover wasn't dreamed up by some massive space agency. It's the brainchild of one single engineering student in South Africa. Just incredible. All right, Section 1, Backyard Mission Control. Let's meet the guy who made all of this happen. So this is 𝗙𝗏𝗃, and while he was a computer engineering student, he decided to give himself well, let's just call it an ambitious challenge. His whole idea was to see just how far he could push really affordable, accessible technology. And look, this wasn't just some side project he was tinkering with on weekends. The 𝗙𝗏𝗃 rover was his actual official honors project at the Cape Peninsula University of Technology. So you've got serious graded engineering mixed with a genuine passion for space. But it's the sheer ambition that just gets me. In his own words, the goal was never just to build a cool remote-controlled car. It was, and I'm quoting here, to exactly mirror real planetary rover telemetry from NASA missions. He wasn't just building a physical rover. He was trying to replicate the entire data pipeline. That is a huge goal. Okay, so how in the world do you even begin to build something that complex? Well, that brings us to Section 2, the rover's 3 brains. You know, you can't just slap one little processor in there and call it a day. You need a really clever setup. And the way he designed it is actually kind of brilliant in its simplicity. It's a 3-board system, and each one has a very specific job. Think of it like this. You've got the master ESP32, that's the main brain, doing all the heavy lifting. Then there's the remote ESP32, which is like the nervous system. It handles all the instant reflexes and commands. And, pretty obviously, the 𝗙𝗏𝗃 camera, well, that's the rover's eye. So, you might be wondering, how does that nervous system talk to the rest of the rover so fast? The secret is a protocol called ESP now. The easiest way to think about it is like a direct hotline between 2 devices. It completely skips the Wi-Fi router, which means you get this super fast, zero-lag connection. And when you're driving a rover, even in your backyard, that's absolutely essential. All right, moving on to Section 3, real satellite senses. Because to really mimic a NASA mission, this thing needs to see and feel the world around it, just like a real space probe would. And this, right here, is the secret sauce. It's all about the 𝗙𝗏𝗃 sensor suite. It's basically a little package of 3 off-the-shelf sensors. But they were chosen very carefully to give the exact same type of data, that telemetry, that a space agency like NASA would be collecting. So first on the list is the GPS. And let's be super clear here, this isn't some simulated data. This little 𝗦𝘃6M module is connecting to the actual GPS satellites orbiting our planet right now. It's pulling down live latitude, longitude, speed, even precise mission timestamps. Exactly like your phone does, but for a tiny rover. Okay, next up is the IMU, or Inertial Measurement Unit. This is basically the rover's inner ear, its sense of balance. It's constantly measuring its roll, pitch, and yaw. But here's the really clever part. It's a built-in safety system. If the rover starts to tip over, say more than 35 degrees, bam, it automatically stops itself. That's how you prevent a catastrophic, mission-ending rollover. And sensor number 3 is this little guy, the BMP280 barometer. And it's a real workhorse. It does double duty. On one hand, it's measuring atmospheric pressure, which lets it calculate altitude, but on the other hand, it's also a thermometer for the electronics. If things start getting a little toasty over 45 degrees Celsius, it automatically turns on a cooling fan. Super smart. Okay, so we've got the brains, we've got the senses. Now for Section 4, controlling the mission. How do you actually drive this thing and see all that incredible data you're collecting? And what I love about the design here is that you get 2 totally different ways to do it. If you just want to drive, get a feel for it, you grab the physical handheld remote. It uses that lightning-fast ESP now we talked about, so it's super responsive. But if you want the full mission control experience, you connect your computer to the rover's built-in Wi-Fi and pull up the dashboard. And honestly, this dashboard is the star of the whole show. It's not just a web page, it's a full-on mission control center that runs in any web browser.
You're getting the live video feed from the rover's eye, all that telemetry from the sensors streaming in real time, and a full set of digital controls. It's the whole package. But just when you think it can't get any cooler, there's this. The dashboard has a built-in AI assistant. It's powered by Google's Gemini, and it is tapped directly into the live data stream. This means you can literally just ask it a question in plain English, like, hey, what's the rover's status right now? And the AI will analyze all the live numbers and give you a full report. That is just next level.
Okay, let's zoom out a bit for our final section, why this rover matters. Because look, it's an amazing piece of tech, no doubt, but the real impact here goes way beyond just the hardware and the code. And to understand why, we have to talk about money. Here's maybe the most important number in this whole story. The total cost for everything, the parts, the sensors, all of it, was about 4,000 South African rand. Okay, now hold on to that number. For perspective, the NASA Perseverance rover, the one that inspired this whole project, its budget was $2.7 billion. The difference in scale there is, it's just mind-boggling. And that, right there, is the whole point. That's the big takeaway. The 𝗙𝗏𝗡 project proves that you can take the core ideas of this incredibly complex satellite technology and make them accessible to almost anyone. It's an amazing open-source tool for students everywhere to learn from. And it's just proof that you don't need a multi-billion-dollar budget to do something truly innovative. So it really leaves you with a pretty powerful question, doesn't it? When you put these kinds of advanced tools and ideas into the hands of creative students and makers, it makes you wonder, what's the next great leap in technology going to be? And what if it doesn't come from a huge government lab, but from a classroom or workshop, or maybe even someone's garage?